So hello everyone. So thank you for attending our today's Rutgers Infusion AI Seminar talk. And today we are honored to have the Professor Tushar Krishna to give us this talk. Professor Krishna is currently Associate Professor in the School of Electrical and Computer Engineering at Georgia Tech. He has a PhD from the MIT, master degree from the Princeton University, and a bachelor degree from the Indian Institute of the Technology. Before joining Georgia Tech, Professor Krishna spent a year as a researcher at the VSSAD group at Intel. His research spans computer architecture, interconnection networks, networks on chip, and deep learning accelerators, with a focus on optimizing data movement in modern computer systems. So I think many of you are familiar with the seminal IRIS papers, and Professor Krishna is the co-author of that paper. And also, besides that, 3 of his papers have been selected for the IEEE Micros topics from the computer architecture. 1 more received an honorable mention, and the 3 have won Best Paper Awards. He received NSF CII Award, Google Faculty Award, Facebook Faculty Award, and the Qualcomm Faculty Award. So now let's welcome Professor Krishna to give us this talk, Teaching AI, the Game of the AI Accelerator Design.
Great. Thank you, Bo. Thank you for the very nice introduction. And thank you all for the invitation and for attending the talk. And please feel free to interrupt me during the talk if you have any questions. And I also have one of my students, Felix, who actually did a lot of the work that I'm going to talk about. He's also called in. So he'll also be happy to chime in with any answers. And of course, feel free to reach out to me offline as well after the talk. My email is listed here, and I'd be happy to continue the discussion. So what I'm going to talk about today is some work we've been doing around the space of leveraging AI/ML algorithms to help with accelerator design. And of course, this is preaching to the choir, like you're all here because deep learning is everywhere. It's shown rapid advancements across several domains: vision, language recommendation, games. And practitioners like Andrew Ng have actually called AI as the new electricity, given how pervasive it's become across science technology. So we're focusing on computation platforms for deep learning now, right? So just to kind of give some context, for training, typically people would use large CPU, GPU, TPU clusters. And for inference, there's a huge interest in developing accelerators. And these accelerators could be on the edge or they could be in the cloud. So why do we need accelerators for deep learning? So at a very basic level, the reason is, there's millions of parameters or weights in models. So AlexNet from 2012 had about 4 million parameters, and more recent models have hundreds of millions to even billions of parameters. And these lead to billions of computations. So very fundamentally, you need a lot of parallel compute in order to run these models quickly. And because you have models with large number of weights and input data samples, there is heavy data movement. So obviously all the inputs and weights cannot fit on chip. So you have to move data back and forth between the DRAM and the chip. And as we all know, the cost of data movement is very expensive. So if you spend about 1x the cost for compute, going to a buffer further away is about 10x, and going off chip is 100 to 500x in terms of energy. So fundamentally, you need to reduce energy in order to run these efficiently. And at a very high level, CPUs are inefficient for the first reason, right? So on a CPU, even if you have a multi-core CPU, you may have 10, 16, 32 cores. So every cycle you can only do 32 computations, while here you have billions, which is why GPUs are very popular, right? GPUs have thousands of ALUs or CUDA cores, which is why GPUs are very, very popular for deep learning. However, GPUs still fundamentally communicate via memory, which is why, from an energy efficiency perspective, they're not very efficient. So this has led to a whole suite of, accelerators, which are often called spatial accelerators, systolic accelerators, data flow accelerators. So the terms are often interchangeable. There's some subtle differences, but at a high level, all these accelerators look like this, right? So you have a whole array of these ALUs or processing elements. In this case, they might just be MACs, which are very tightly coupled. And the idea is that, since we have billions of computations, let's spread them across these hundreds of ALUs so that every cycle we get, a lot more throughput. And to avoid data movement or to minimize data movement, let's try to reuse the data within the array. either via, local storage within the PEs or across this memory hierarchy, and via direct communication. So this reuse is what gives a lot of efficiency to these accelerators and avoids data movement. So with this, 100-foot view, let's kind of dig a little bit deeper into the architectural components of a DNN accelerator. So an accelerator really comprises of two key sets of components, right? So there's the actual hardware resources. So the number of processing elements, the buffer sizes, the NOCs that are connecting these, and the mapping, right? So how do you actually take your DNN model and map it onto the accelerator? How do you tile it? How do you order the computations? What's the parallelism mechanism? What is the shape of the array? And these things are together called data flow. And so, of course, this is pure hardware. Some of this could be in hardware, some of this could be in software. So this really depends on how flexible or programmable your accelerator is. In some accelerators like Iris, all of this was, hard coded into hardware. The data flow is fixed, while more recent accelerators allow you to program the data flow on the compiler. But ultimately, these two components are what determine overall energy efficiency and performance of your accelerator. So how do you build an accelerator, right? So what you would do is, you have a DNN model or a class of DNN models you're interested in, and you would build an accelerator for this, where you care about the resources and the mapping. But the challenge is that, models are becoming highly diverse, right? So deep learning kind of kicked off with CNNs, and then we got interested in RNNs and MLPs. And recently there's a huge interest in transformers. GNNs are becoming popular, and sparsity is becoming very popular, right? So DNN model diversity is increasing. The task diversity is also increasing. There's state-of-the-art DNN models kind of getting developed almost on a daily basis if you track the papers on arXiv. There's a lot of diversity in the hardware platforms itself. So as deep learning becomes pervasive, deploying on the IoT or the edge or the fog or the and depending on cloud versus edge versus embedded devices, the hardware resource constraints might be different. And there's, accordingly, given all of this, the map space also increases. So if you want to find the best mapping for a given model, if you kind of map at a model granularity, you might need, T minutes for each model. But if you kind of want to map at a finer layer by layer granularity, this would grow exponentially with the number of layers, right? So this challenge is growing. And so essentially what that means is, if you are designing a model, given the platform, the area, budget, technology, you kind of try to identify the high hardware resources, you do some design space exploration, come up with the mapping, right? So a typical, SOC, timeline of like 6 months to a year, you'll have to do all of this, come up with the most optimized accelerator. And often what's done today is that a lot of this design space exploration is based on heuristics, right? So you're going to manually try to tune the number of PEs, buffer hierarchies, run your simulator a few times, classic computer architecture, right? Like balanced compute and memory. But now you also need to come up with the best mapping. So this is also often very heuristic based today. Given a kind of DNN models, you might come up with the best mapping strategy. So Iris, for AlexNet came up with row stationary, and NVDLA identifies that ResNet has many, many deep channels, so tries to model channels in parallel. So there's a lot of, data flows and mappings that have been tuned to the kinds of models we're interested in, and often using heuristics. And then the accelerator itself, again, this deployment, the optimization for both of these might depend on the end use case, whether you're designing for an ASIC or an FPGA, whether it's part of an SoC, whether it's an IoT device, right? So all of these will increase the design complexity here. And so this limits the time from, let's say the latest transformer model being developed to an accelerator that can run it efficiently, right? And so the accelerator might actually become obsolete by the time it launches because the model has changed. And this is certainly an example for something like Iris, right? So if Iris was designed for AlexNet and today, AlexNet is not being used. There's massive engineering cost, and we often rely heavily on human experts, right, in order to navigate this. You really need to understand the model. You need to be an architect who understands, hardware resources. You also need to have some compilation experience to understand how mappings work. And oftentimes, since you're optimizing all of this manually, like your performance might actually be suboptimal. So the question is, well, are these limitations problematic, right? So, I mean, this is how we've been doing even CPU design, right? It's not that it's fully automated. There's a lot of heuristics used there. The challenge with accelerators, though, is, right, as I mentioned, this field is changing very, very rapidly. So you might have a DNN model, you have a new platform that you're targeting with a specific area power budget. You have some specific objective. You're targeting a self-driving car, real-time latency is a metric. You're targeting a data center, throughput is a metric. Then the deployment scenario itself, whether how you're kind of trying to cluster these into larger platforms. The service scenario, whether you want to run a single model at a time or whether you want to do multi-tenancy, right? All of these things might come in. So suppose I have this scenario, I come up with some accelerator, then my scenario changes. I have a new model. This time I'm trying to go for throughput, IoT, and trying to support, let's say, multi-tenancy. Now I have to kind of run this entire design loop again, do this whole optimization, come up with a new accelerator. And as this changes, right, like the time will obviously keep increasing. And so the problem is, as models become pervasive, as technologies become pervasive, this loop of design, like algorithm design to hardware, is becoming more and more expensive. So that's kind of the focus of this talk, on trying to see how we can make this way more automated. So with this, this is going to be the outline of my talk. I've given you guys a very brief background on DNN accelerators. I apologize for going through this very quickly, but I think I've tried to identify the key pieces that you'll need to understand the rest of the talk. Next, I'm going to talk a little bit about the design space. I've talked about hardware mappings. Let's try to understand what exactly is the design space, which will also tell us why it's so complex, right? Why is it so complex to automate it? Then I'll talk about, given time, like 3 methods that we've developed actively for, using reinforcement learning and specialized evolutionary algorithms for navigating this design space. And then I'll kind of end with, takeaways and some future work that we're looking at in this space. And some of these papers are kind of, from where each of these pieces have come. So let's try to understand the design space. So as I mentioned, right, for an accelerator, there's really 2 pieces. There's kind of the hardware design space and the mapping design space. And I mentioned, like, this could be in hardware or software, depending on flexibility. So, so you have a workload, you map it, you have an accelerator. So the hardware design space is number of processing elements, the buffer sizes and the NOC architecture, right? And on the mapping end, you kind of have 2 pieces. So you have kind of your data computation and tiling. So you take your workload, you have to tile it down into tiles for, let's say, the inputs, filters, and outputs. And then you have to schedule these tiles, right? So the scheduling will involve the ordering. So you would have heard terms like wait stationary or output stationary. This is really about the ordering of the tiles, right? Like what goes in the outer loop, which is the slowest one. The parallelism dimension, like how do you kind of parallelize these tiles across the accelerator? And what is the mapping shape? Like the number of, by mapping shape, I mean the number of levels of parallelism, right? Like, do you have a 1D accelerator, a large vector engine? Do you have a 2-dimensional array? Do you have a multiple 2-dimensional arrays? So this will determine the number of levels of parallelism you can essentially get. So it's related to parallelism. This is the specific dimension, and this is the number of levels of parallelism. So we kind of break them down into these components. So given just this design space, and some of it is interrelated, I'll talk about this. The hardware design space that you're targeting, as I mentioned, depends on deployment, right? So I've mentioned this already, right? So given a model, you might have an accelerator template in mind. So you are NVIDIA and you have an NVDLA accelerator template in mind. NVDLA is essentially looks exactly like this. And you have the output channels in one dimension, filters, input channels in the other dimension, and you have these codes that are doing dot products and adding them up. So now that you have a template in mind, of course, for the hardware resources, you need to decide how many Ps, how many buffers, and so on, right? So this will depend on the scenario I mentioned, right? So edge versus cloud, whether you're trying to schedule a layer by layer, or you're trying to do pipelining of multiple layers on the accelerator at the same time. And this might lead to different implementations. So you might have an implementation where for the same accelerator, I decide to have 8 PEs and 19 buffers, divided up like this, let's say for the weights, activations, and outputs. Or I have another accelerator, which is larger. So here I have 16 PEs, here I had 8, here I have 16 PEs each, and there's 39 buffers per PE. And of course, the L2 sizes change as well. So depending on this, the specific implementation might change. And this matters. Like if we look at some of the layers from MobileNet here, what you'll notice is, so here I've plotted, area on the x-axis, latency on the y-axis, and the colors represent Ps and buffers. So for a given area budget, let's say I have, 2 micrometers square, and I wanted this latency, then I would need like so many buffers, for this performance and so many number of PEs. But if I look at a different layer for the same area, budget, and performance, I might need different number of PEs and buffers. So the relative sizes actually matters, and it varies across different layers. So optimizing for this is important. So that's the impact of hardware resources. What about the mapping, right? So I mentioned that mapping has these 4 components, right? The compute order. This will determine the amount of reuse you get. Parallelism will determine spatial reuse opportunity, right? Number of parallelism levels will determine, like, again, how much concurrency you can get. And the tile sizes will determine the buffer size within the PEs. And all of this will affect, latency and energy, right? And you might have accelerators where you can have flexibility, right, in hardware to program all of these in. Because of different DNNs and implementations. And again, like, I'm not going to go very deep into this piece, but if you're interested, you can please go ahead and check out the synthesis lectures that I co-wrote with some of my collaborators at NVIDIA that talks a lot about the idea of data flow. But the thing I wanted to mention was, again, the fact that, the mappings actually affect performance, right? So here, the search space of mappings is really large. Like if you have single level of parallelism versus 2 versus 3, the search space will be the sum of this. And here again, I'm plotting like energy versus latency and latency versus area. And the key takeaway is that, across these different mappings, right, for the same layer here, essentially they can be like millions or trillions of mappings, and they can be 4 orders of magnitude difference across different mappings. So trying to find the optimal mapping is crucial. Okay, so we have, diverse hardware choices. We have different mapping choices. Like, how do we actually model this and evaluate whether, for a given hardware and for a given mapping, how well would the DNN model work? So for this, there's a lot of work in the community on creating cost models. And so I'll just point you to some work we've done in this space. That's what we'll be using for the rest of the pieces in my talk. So this is a framework called Maestro that my student Hyokjin had developed. So you have a DNN model, you have your hardware accelerator with certain number of hardware parameters, and you have a mapping. And this is, Maestro's way of describing the mapping. I'm not going to go into this, but essentially it tries to describe all the key features, right? So the computation order, the parallelism dimension, the number of levels of parallelism, and the tile sizes. So this kind of captures a very unique mapping. So for a hardware, for a given unique mapping, Maestro will actually determine what is the runtime, like it will determine all the reuse that you can get from hardware and determine the runtime, throughput, and energy. So if you're interested in checking out Maestro, I'll point you to the Maestro website for more details. Okay, but for the purposes of this talk, Maestro is this black box cost model that, given a hardware configuration and mapping, will tell us how good it is. And so we're going to use this to now start doing some very efficient design space exploration. So let me pause for a second here and see if there's any questions at this point. Like, the aim here was to just give you all background to now go in deeper into the specific DSE methods. All right, so let me continue. Again, please feel free to interrupt me if you have any questions. So we would like to, now search for efficient hardware and mappings automatically. That's what we want to do. And so first, let's try to understand the properties of the design space, right? So I mentioned the hardware design space. I mentioned the map space. One of the challenges I've mentioned a few times is that the space is really large. So for a given DNN layer, there can be 10 raised to 36, valid choices for mappings on an accelerator, assuming that the accelerator is fully flexible, right? I mean, it can run any mappings. Like, there are all of these valid mappings, which are definitely not amenable to exhaustive search, right? So if you did exhaustive search, you would require time that is longer than the age of the Earth. So clearly, sample efficiency is crucial. And this is why a lot of times people just use heuristics, because, you can't search. But we want to develop search methods where we can actually search very, very quickly, right? Within a few search samples, we can actually find a good mapping. The other challenge, and this is something prior works like mind mappings have also pointed to, is the fact that, this design space for hardware and mappings is highly discrete and it's non-convex. So given like a specific input, like the reward, right, or the performance that you might want to get is non-convex, which means you can't just, apply like gradient descent and get to the most optimal. So you need some gradient-free methods or reinforcement-based methods in order to search through this space. So let's try to understand, how these methods kind of compare, right, at a very high level. So So as I mentioned today, typically you would use manual methods or heuristics to search through these. So there's no search happening. You kind of come up with some design point or do some specific number of searches. So there's no notion really of optimality, and there's no real notion of sample efficiency. I mean, you're just, there's a heuristic that you're running. There's a lot of population-based algorithms like genetic algorithms, evolutionary strategies, which are known to be very good in terms of, overall optimality because they search through the entire space, but they have low sample efficiency. While deep reinforcement learning is very popular these days, this is known to have much higher sample efficiency, but easier to fall into local optimum. So this chart is trying to, at a high level with a cartoon, it demonstrate what I mean, right? So if this is the entire design space, a manual method will just pick one, right? Or some of these, and this might be quite suboptimal. Here, we would like to get to these dark red ones, and we just happen to pick a suboptimal one. Reinforcement learning is great from a sample efficiency perspective. It's going to, just very quickly go through a few samples and converge, but it might actually converge to a local minima at this red, light red point. While population-based methods are going to be, much more they're going to do a much larger search, but they might be suboptimal, right? So they might not be sample efficient. So I see a question on the chat. So since I'm not able to open it, if you want to ask it, or if Bo wants to interrupt me and ask, please go ahead and do that. Is there a question or?
Yeah, okay. We have a question in the chat box. You can either answer right now, or you can answer it at
the end. So let me just come to it at the and let me just. I'm worried if I open this, will this? Okay, yeah. Okay, so there's a question about accelerators like NVDLA and Iris support a fixed data flow. However, they are not optimal for different heterogeneous workloads. How much reconfigurability would you want to adapt? How would you decide? So this is a great question. This is actually so. So this is actually a very active area of work we are doing. So this is a little bit different from this specific talk. So I will definitely talk about this at the very end, but that's a great question. Hold that thought. So far, I mean, in some sense, I am motivating that you need to find the right hardware parameters and data flow. But I think what you're alluding to is something where we are trying to also find, how much reconfigurability or flexibility do we add in hardware. So this design space is assuming that you have full flexibility, while this point is assuming you have no flexibility, right? So in some sense, we have one extreme here. This is where Iris or NVDLA would fall. While what I'm going to talk about is assuming you have full flexibility, you can search. And what is kind of the right balance is where the tools that I'm going to describe will help, because they will let you kind of fine tune and find the appropriate one. So even though this talk doesn't go into it, we also have some versions of these tools that will kind of do a search in a somewhat of a restricted space that tries to weigh the cost and benefit. So, so that's the broader point, but I can have a longer discussion as well offline if you're interested. So, so as I mentioned, right, so DRLs are very popular these days for high sample efficiency, and that's why they've been used for things like the alpha. I mean, they're very good for games, right, where you have a huge search set of possible states. So what we did in this, and what we are going to try and do is, try to see how well these methods apply to this search space and see how we can optimize these methods more to work even better. So this is kind of the proposed accelerator design optimization loop that we are developing. So I have some problem or design space here, right, that I'm looking for. It might be hardware, it might be mapping, it might be both. And as I mentioned, we're going to use Maestro as the evaluation method, and we're going to develop some exploration method and connect them all in this closed loop to create an automated flow. So I have a model, I have some objective, I have some constraints. Was there a question? Sorry. Okay, so I have a model, I have some objective, I have a constraint, and this is the optimization loop that I would like to design. So I have, I'm going to develop some method and try to evaluate how good the mapping or the hardware is, and keep doing this till I converge or till I've run through a certain set of sample points and come up with the optimized solution, maybe a mapping. And so this is the framework that we're going to try to do for different kinds of problems. So we have some interesting work that we've been doing in this space. So I'll talk about Confucius, which actually uses an RL-based exploration method for hardware search. Then, Gamma is a genetic algorithm-based method for mapping search. DiGamma is a hardware plus mapping, is a genetic algorithm-based method for hardware plus mapping co-optimization. And Magma is some work we've recently done, which is for the problem of multi-accelerator scheduling with a GA-based method. And I'll kind of, acknowledge my student Felix, as I said, who's been the primary person driving this entire line of work in my group. And so today I'm going to essentially talk about these three pieces, but I do encourage you to, just, of course, encourage, like, check out our HPCA paper as well. But I'll not be able to go into that today. So these three techniques are, these three works that I'll go into will kind of give you a glimpse of how we went about designing RL and GA methods for this search problem. Okay, so with that, let me first dive into Confucius. And for all of these methods, like, you feel free to check out the paper for more details, and all the codes are also open source and released. And so feel free to check them out and use them for your own research. So coming back to, again, this figure of the design space, right? So this is what we would, this is the design space of a DNA accelerator, PEs and mappings. And in this first work, we are going to try to explore the hardware design space. The mapping space is going to be constrained. Like, so the data flow is going to be fixed. So here, related to the question that was asked, imagine that I am designing an NVDLA accelerator. So the data flow is fixed. I know it is the NVDLA-like data flow. My tile sizes will be flexible, so I can, like, change the sizes of the buffer. So the tile sizes kind of, directly affect the buffer sizes. So this is where there's a relation between the map space and the hardware design space. So I'm going to change buffer sizes, which in turn means my, tile sizes are flexible. And I'm going to explore all of these choices for a given data flow, right? So as I said, the use cases, I want to design the, like, NVDLA 2.0, for example. So again, the high level idea is, as I mentioned, right, the search space for all these choices is really large. And so what we are going to do is we develop like a two-stage optimization method, where the first stage uses reinforcement learning for, choosing between some number of PEs and buffers. And we kind of create an action space where we limit this first to 12 different values empirically for kind of, simplifying the problem a little bit. So, like, you have these 12 choices for PEs, 12 choices for the buffers. And so this means, there is like 12 square choices for PEs times buffers raised to n, right? Like, because we would like to, so we are trying to design an accelerator where the entire model is run in a pipeline manner. So I'll describe that in a bit. But so the idea is we would have 12 square choices for PEs and buffers for each layer, and there's n layers. And so we want to run the entire model. So this is the search space that we are going to look at. Which would essentially be, this size, and it's still large, right? So that's why we want to use some optimization method, and we're going to tailor RL to drive the search process. And then we have a genetic algorithm as the second stage to fine tune the result. So suppose you come up with a specific solution, let's say 8 PEs and 49 buffers. Since we did a coarser search here, we're going to fine tune it more to come up with a more optimized design. And so in terms of the design space, this is what it means, right? So if I say, 19 buffers, this is what it would mean. 39 buffers, just as an example, this is what this means. So because of the design space, again, being large, the algorithm is not promising optimum. At least so far, we've not, there's no optimum guarantees here, but it optimizes the solution with high sample efficiency, as we'll see in our results. So the way Confucius works is the following. So I have this two-stage method, RL-based coarse grain search and GA-based fine tuning. So I essentially, create this RL loop, get the hardware resource assignment from RL, then send it through a customized genetic algorithm to fine tune it more. And this will give me the final solution, which says, okay, for each layer, how many PEs and buffers are optimal to run to get the best performance. And this entire framework is what is called Confucius. And the input will be, again, as I'd shown, this higher order figure, right? So the DNN model, whether you're trying to do pipelined or serial deployment, the objective constraint, and whether the data flow here, as I said, is constrained as well. So how does RL work? So many of you might be familiar with this, but suppose I have an RL agent learning how to play the game of Super Mario Brothers, right? So the agent would take an action, maybe it asks Mario to move forward, Mario gets some coins, go as a reward to the agent. Then and the specific state also goes to the agent. Then the agent asks Mario to jump up. Mario gets a mushroom, gets some reward, keeps moving, but ultimately dies, right? So essentially, you play the game, all these rewards gets accumulated, and the agent updates its own policy to try and play the game better the next time. So in our case, the environment is a hardware design, is an accelerator cost model, specifically Maestro, for determining how well I am playing. And the game I'm playing is to do hardware resource scheduling, right? So I'm going to show this with an example later. So essentially what we are trying to do is the following, right? So the game we are trying to play is hardware resource assignment, where given a power area budget, we want to find the number of PEs and buffers for each layer in a layer pipeline deployment scenario, such that, and layer pipeline means the following, right? I mentioned, so all the layers are mapped in a pipeline manner over the accelerator, and I want to, minimize some objective like latency. So the RL algorithm that we will have is each step, the agent will assign some PEs and buffers to a layer, see how well I do, and the environment will track the remaining power area budget. Then each episode, I will essentially run the entire DNN, right? Essentially multiple steps. So I do the entire layer until the environment terminates. And if the environment will, like the game will terminate either when the entire DNN is run or the environment runs out of area or power, right? And then multiple episodes will be run, right? So the same game is run over and over again till the algorithm converges, or if I have like some fixed number of episodes that I've given as an input. So just to go into details, suppose my objective is latency or energy constraint. So what I'm going to do is the action is number of PEs and buffers. Maestro, as I said, is the model, is the environment. The reward is the latency or energy. And if I violate the latency or energy, there's a huge negative penalty. So a negative reward if you violate whatever was the target you were like, if the constraint is violated. So if you exceed the area and power, then you get a negative reward. And the observation or the state from the environment is what is the current DNN layer, what was the last action, what is the current status, and so on. Okay, so now let's see what the agent will be, right? So this is how I formulate the problem of hardware resource scheduling. What is the agent? So, so for the agent, essentially, there's a lot of RL algorithms out there, and the paper goes into the exploration of many of those, but the final one that we used had a policy network architecture that used an RNN. The RNN kind of the time series thing helped us capture the fact that each layer is dependent, and we use reinforce as the policy network update, and there's no value function here. And again, the paper goes into a little bit more detail on the RL part of why this kind of a network seemed to work well. Okay, so how does this scenario work? So in the first episode, so suppose this is my design, right? So I have some constraint, which is coming from area, right? So I can have a maximum of 20 PEs and 20 buffers. And the game again is, how many PEs and buffers per layer. That's what I'm trying to learn here. So I start the game, for the blue DN layer here, suppose the action that the agent says is 12 PEs, 4 buffers. And I evaluate it using the cost model, and I get some reward, let's say 32. Then for the next layer, again, I get some other value, 12 and, maybe 9 and 7. I get some other reward, 13. And for the last layer, now I get 4 and 6. And now notice that if you add up 12 plus 9 plus 4, this is actually more than 20. So I have violated the PE constraint here. And so that's why I'll actually get a huge negative reward. So that's basically the agent telling that, this did not go very well, and like, you actually violated. And so your reward overall is much more negative. So accumulated reward is now minus 55, right? And so this kind of tells the agent, it updates its state, and I've tracked like the record and the episode. So I move on to the next episode, play the game again. This time, the agent maybe does better, and plays this game again, and this time comes up with a reward that's more positive. So the reward is increasing. So really we want our reward to keep increasing, right? And converge. So eventually I play this for a while, the reward converges. So the RL phase is done. So the first phase is done, and I have come up with some resource assignment strategy. And now I fine tune this using a genetic algorithm. So I essentially, I came up with 60, in this example, maybe, 64 PEs for the first layer and so on. And I essentially, since I have 64 PEs, I essentially maybe during the fine tuning stage say that let's try to just evaluate close to this. So I go, plus and minus 4 and evaluate from 60 to 68 PEs, right? Remember that the problem with genetic algorithms was that it's not very sample efficient. So if I threw the entire problem at a genetic algorithm, it would have kind of, just kept jumping around, right? So here I use RL to converge on a space and then use GA to explore just that space. And so now, this comes in to the genetic algorithm. I'm not really going to go into the encoding too much, but these are different genes and genome. So I have like genes for each PE and buffer, and like the number of genes is the number of layers here. And so, and now I do some genetic mutation, right? So I mutate these values. I can go up to ±4 for the PEs and buffer sizes. And I also have a crossover where I can swap. So remember that the total number of buffers cannot be exceeded now because that's been my constraint. But I just swap the number of buffers. So maybe I swap, maybe swap in this example number of PEs. So I, instead of the first layer getting 66 and 96, I try what if the first layer got 96 and the other layer got 66, right? So I play around with some of these operators to fine tune using crossover mutation to get to a solution that's more optimized. And so on, right? And finally, I will get the most optimized solution after running GA for a while. So let me show how all of this kind of works in terms of the results. So we tried, we compared Confucius against a bunch of RL methods, also other optimization methods like random search, grid search, Bayesian optimization, and a simple just GA overall, and ran several DNN models, gave different constraints and so on. And I'm going to show results with the layer pipeline scenario. And this is kind of a snapshot of the results. What I wanted to highlight was so this is, y-axis is latency here. There's different constraints for different kinds of hardware platforms. But without going into that, the key thing I want you to notice is for a lot of methods, they never even converged within a set amount of time. So GA, for example, didn't converge here. Random did not converge in some of these cases. Confucius was able to converge every time and consistently find better solutions with same or better performance than the others. We also compared, Confucius, which is using like reinforce against other RL methods like A2C, actor critic, and so on. And again, the key takeaway was all RLs were able to find valid solutions, but reinforce-based Confucius was actually 4.7 to 24 times faster, and again found better, similar or better solutions with less search time. Yeah, again, as I said, I'm not going to go in too much into the details of the RL. And this is the piece I wanted to highlight about how local fine-tuning helped. So this is, the global search, which led me to this solution, and then fine-tuning actually allowed me to get to a solution that was even better. And this is again just kind of highlighting, the optimized value versus the initial value. But overall takeaways were RL, on average across all our experiments, RL was able to optimize the result by 74% and GA further by 33%. And this is an interesting snapshot of, again, related to why, a method like this is valuable, right? So notice that if I had a heuristic, I might have just given the same number of P's or buffers, or, tried to just design that based on some heuristic. Using this, we actually found that this is an example for MobileNet, V2 running, as I said, an NVDLA style data flow. The number of PEs and buffers per layer was quite different. And in fact, we noticed this trend where, the depth-wise layers got, less resources than the other layers. So it intuitively makes sense. And it's interesting to see that the algorithm actually learned this and was able to actually find solutions doing this. We also did some experiments on generalization. So, so I have trained the RL agent once, right? And it's played the game, and let's say it learned what's the best allocation for VGG16. Now let's kind of try to, have it determine the best allocation for ResNet, right? So instead of starting from scratch, what if I actually started from the solution that VGG16 had, or like AlexNet had? What we saw was it was already much better than, just starting off at some random or heuristic point, right? So the takeaway was that, this is given that we've kind of tailored it to, again, in this case, maybe CNNs, then starting with a solution for another CNN actually led it to converge much faster. So this was actually very interesting, which can allow us to maybe do warm starts for this algorithm, right? Of course, this might not, like if you have something that learned the optimal allocation for a vision model, that might not be the the best for a language model. So this is also something we saw, but within the class of, let's say, vision models, this trend exists. So this was also something very interesting. So just to kind of summarize Confucius, it is trying to, do hardware resource allocation, reduces design time. I mean, the like end-to-end flow took about 30 minutes, right? So push button, 30 minutes, you get a hardware allocation, much less, engineering effort. We abstract out a lot of low-level details, so any non-expert can also run this and design their accelerator. And we found 1.5 to 10x better latency energy than existing fixed, hardware and mapping designs. All right, so with that, let me jump into the next method. I noticed that I may actually have to go through this a little bit quickly, so I apologize for that. But again, I'll be happy to answer more questions on this. I do want to leave some time at the end for questions. So let me go through this piece a little bit quickly, just to give you a glimpse of what we are trying to do. So here we are trying to now search for mapping space rather than hardware design space. So here the hardware is now fixed. So you have an accelerator that you built. You have a hardware that is given to you, but we are assuming this is a flexible accelerator. So rather than a fixed, iris or an NVDLA, this is an accelerator that can run any data flow. So the data flow choices are completely flexible. The tile sizes are constrained, right? So they're flexible, but they are constrained because my tile cannot exceed the size of my buffers. So I can still explore tile sizes. It's just that if they exceed this, that's not valid. And so we want to design something that can explore this. So this is fixed, this is explored. And the high level idea is something I've mentioned, where since the shape of mappings is non-smooth, we notice that, simple changes can actually lead to huge spikes in performance. So if you simply change the loop order a little bit, right, which will effectively mean you swap from, let's say, wait stationary to input stationary, right? Or, and so you will actually see huge spikes in performance. Tile sizes also show huge oscillations, especially due to edge conditions, right? So if you have a tile size of 65 for an NVDLA, which can only run 64 channels, you'll suddenly need 2 iterations. But a tile size of 63 will be able to run in 1 iteration, right? So minor changes can give huge spikes as well. And so we actually could not get RL to really work well here, and it did not converge. I mean, in general, we have a few kind of thoughts about why that happened. So we developed a more sample efficient genetic algorithm for this. And so what I'm going to do maybe is very quickly, as I said, go through. So in a conventional genetic algorithm, what happens is you have a notion of genes and genomes. They essentially go through all these steps related to crossover. So you have a gene and genome from the first generation. You crossover, generate a second generation using parent genomes. Then you mutate this, which means perturb the values a little bit. And then so these mutated genes are then sent through, an evaluation stage to get the final evaluated value. So this evaluated value is now again fed back. So once you have all these genomes that you've evaluated, so you have, let's say, 10 candidates, right? So this might be 10 mappings. You evaluate all of them, you find the best set of mappings, use those as parents and create, n new mappings, right? So that's the basic idea. So I will essentially now sort these based on how well they did, come up with, a set of scores, sort them, create parent genes, and again, send this through the same loop. And so now create, using the best mappings, create n more mappings using some crossover mutation and so on. So this is the basic idea of GA, right? But the challenge, so what we do in Gamma is that we actually modify a classic GA by adding more operators, which are tuned to this specific design space for mappings. And I'll describe that briefly in a second. So this is a classic genetic algorithm with crossover mutation. Gamma adds some more operators. And again, the overall flow is very similar, right? Inputs, DNN model, objective resources, some mapping constraint. You run this through this loop, and eventually you'll get some optimal mapping strategy. Okay, so now let's come into some very interesting things that Gamma does. I want to spend a couple of minutes on this slide. And if you understand this slide, I think that's really going to be great in terms of kind of identifying what we did here. So what we did was try to create the mapping space using a genetic encoding. What do I mean by that? So essentially, if you think of a loop order, right, this is essentially a loop order for CNNs. This is, let's say, a specific mapping. we encode that in this following manner. So I have 6 genes here, one for each dimension of the loop. I'm assuming batch size of 1. So 6 dimensions for convolution. So these are all genes. The order of these genes is the compute order. The value of each genes is the tile size. I have another 7th gene, which is the parallelism dimension. So notice that I have tile size, compute order, parallelism dimension, right? So I have created 3 parts of a mapping by this one genome. And then I actually, paste multiple genomes together to create the full mapping space. So here, this is the mapping within the PEs. This is the mapping across the PE. So in some sense, now I have like 2 dimensions here. So now I have captured, compute order, tile size, and parallelism dimension, and the number of parallelism levels is the number of genomes. So this entire thing together is capturing a mapping. So as an example, if I wanted to design an NVDLA like accelerator and a mapping for that, this genome, like this, these 2 genomes are precisely specifying what the mapping is. It's saying that, I have the C dimension spatially mapped here as one of the parallelism dimension with size 64. And these are, these are the KCRSYX values inside the P's. And then I have the K dimension mapped as the second dimension. And across this, I have, K equal to 1, C64, and these are the tile sizes, right? So 2 levels of parallelism parallelized across KC is something this very precisely specifies. And so now what I do is to search for mappings, right? So this is a mapping, and now I want to design a very specialized genetic algorithm to search through this space. So what do? I essentially, create like these very specialized operators. So my crossover operator, let's say these were 2 mappings that worked well in the previous generation. This is a dad genome and a mom genome. I essentially do a crossover. So in the son, the son gets the same dad genes, except that this one comes from the mom, this one comes from the mom, right? So it's the same mapping, but slightly perturbed, but perturbed in a way that, it is from a mapping that was actually good, right? Similarly, the daughter genome genome has like the mom genes, except for 2 dad genes. So now these 2 candidates are slightly different, and maybe they'll be better, maybe they'll be worse, right? So that's what crossover would do. And then I do some tiny mutations. So I change the tile sizes a little bit. I have another, as I said, operator called reorder. This is a very specific kind of mutation where I reorder these 2 genes. Remember that the order of the genes was the compute order, right? So here, if I reorder this, I'm kind of switching between, let's say, a weight stationary to an output stationary to an input stationary, or whatever, like channel stationary to filter stationary. Right? So I'm kind of doing all of that by just changing the order of these genes. That's this mutation operator. This mutation operator is changing tile sizes. Then I have more operators. I have an operator for growing, right? So I mentioned that I might have multiple dimensions of parallelism. I have, large vector or like 2D array, or I can do maybe multiple mapping. So depending on the accelerator flexibility, I might be able to do any of this. And so I have an operator to study that space. And I have one more operator to shrink as well, right? So I can go from, 3 level to 2 level to 1 level. This is just a summary of, how these operators allow me to explore the entire map space. And as I already mentioned, the cost model is Maestro. Let me go through this a little bit quickly and just jump to some key results and takeaways. I mean, the key takeaway was the fact that we designed this special algorithm, it allowed us to find solutions across different scenarios. Again, converged, worked actually much better than different methods. And, this is kind of just showing its convergence across several layers. The interesting thing was that we were able to find very different mappings for in this case, ResNet. We found that, for a medium layer, it decided to get a 3-level mapping. For a late layer, it decided to have a much larger K. For an early layer where, here there is much more number of channels, right? So that's why I decided to choose a large tile size. For an early layer, it decided to parallelize with small tile sizes. So a very interesting, and so some of this is actually consistent with, some of the heuristics and intuition. And it found very unconventional tile sizes and U2 borders. So reduced design time, engineering, less engineering effort, better performance. All right, so next, in the interest of time, I'm going to skip digamma. So digamma is an extension of gamma that actually tries to search for both mapping and hardware together. So it's pretty cool where it has another gene that also tries to capture hardware. And so you can kind of search for hardware and mappings together. by, but I'm gonna, as I said, skip that and go to just maybe a summary. As I said, like digamma does both. And I wanted to maybe just talk a little bit about some takeaways, right? And then leave the floor for questions. So one of the challenges, as I mentioned, is, large design space for DNA accelerators, trillions of choices, and this space explodes with models, deployment scenarios, and it's, non-convex, discrete, irregular. So we can't run gradient descent. And so sample efficient search methods are crucial. And this is where we believe that domain-aware ML methods have a lot of interesting opportunities. So this is maybe the key takeaway I wanted to present from our learnings through, 4 projects in this space. So what we noticed was, if the design space is completely unknown, then you can take some black box method like reinforcement learning, GA, and throw it at it. And there's different trade-offs of what works well when, but they are not very sample efficient for this space. So they didn't work as well. But because if we know the design space, here we know we are searching for mappings, we can actually tune the algorithm to be much better in terms of searching, right? So in gamma and digamma, actually, we create very special operators. The crossover is not the classic crossover and mutation of genetic algorithms. It's really tuned to find the best mappings, create minor perturbations. And there's also mechanisms to, change the map space dynamically. And since we understand how hardware and mappings are correlated, we know that the buffer size directly correlates with tile size and so on. We can actually, again, kind of tune the operators to, be much more sample efficient than just randomly finding actions through RL or GA. So that's something we found very useful. And I just kind of will leave you all with this slide. So next steps, we are actually trying to now understand some of the optimality and like visualize how well these methods are working through the design space. And we're also trying to see if we can just generalize rather than running the search over and over again. Can we learn from some searches and then just recommend optimal mappings in a one shot without any search? So thank you. With that, I'm going to stop and I can take more questions.
Thank you, Tushar. Thank you for excellent talk. Actually, I have several questions, but I would like the audience to ask first. So any questions from our audience?
Yeah, thanks, Professor. I have a small questions. So the first thing to start with is like, I'm curious to know like how did you evolve to get to the point like using genetic algorithm over reinforcement learning? Like what was the process? Like how do you figure out that, okay, genetic algorithm is working the best over the reinforcement learning?
Yeah, so I mean, so in some sense, I think, it was, I would say, maybe more trial and error. So, but also I think some domain knowledge about the algorithm itself, right? So, and I'm sure like if you have, Felix can answer in more detail, but in terms of the process itself, I think we kind of started with, okay, we would like to do design space exploration and let's look at optimization methods. And I think RL kind of came naturally, right? I think a lot of people are using RL for different kinds of mechanisms. So we started with RL. The challenge in RL is that you need to be able to model the problem as a Markov decision process. So if you're able to do that, it works. So in the case of, the hardware design space one, we had like, we were trying to allocate one layer after the, like for each layer, we were trying to allocate P's and buffers. So we're able to model it as the series of processes, which worked well. And then RL was something that we were able to apply. In general, genetic algorithms are much more easier to apply, because all you need fundamentally is for each thing that you're searching for, right? You can have a gene for that. So if you can have a gene for each component you're searching for, and have the gene have any value, right? Very valid value, and use these operators. So genetic algorithms are kind of easier to kind of design and deploy. So for the hardware one, RL worked well. For the mapping one, we started with RL. It did not work well, wasn't converging. We started with standard GA that was also not really converging, and then kind of that evolved to something that is more domain aware. So I mean, maybe just a lot of, I would say, hit and trial, and also maybe some understanding. I know, as I said, Felix is an expert on trying to see, okay, from literature, there is kind of understanding of what kind of games RL works better for, what kind of things GAs work better for. And again, my key take is, let's try to understand how well the design, like understand the design space, see what method maps well for that, and then accordingly pick that, right? Because a lot of it is also engineering to get this method to work. So that's the process we followed.
Yeah. Okay, thanks a lot. I have a few more questions. Like I'll wait for someone else to ask.
Hi, Professor. I also have a question. So for the hardware schedule, we are actually doing allocation for the constrained hardware source for the layer pairs. So I'm wondering whether this optimal solution is unique. Like, is it possible that for like the allocation for each layer, one option is for each layer it's better, but we have a less layer pairs and opportunity, or we have another option that's maybe for each layer it's not best, but we can
but
have
overall,
yes.
Yeah, you're right. So in general, I mean, not just for the hardware scheduling, but even for the mapping one, I will say that there are so there's not just one optimal solution. There's many solutions that have very similar, and it also depends on what you're optimizing for. So what we've noticed is you'll have many solutions that give you the exact same performance, but are differing in terms of their energy requirement, because some of them just happen to have more local accesses to a local buffer versus a global buffer, and vice versa, right? So if you're optimizing for latency, then many solutions will have the same value, but energy will be different, and vice versa. So there's many solutions that have the same performance, which actually then this is where we are very interested, and it ties to one of the questions that came in the chat, right, on how much reconfigurability do you add, because you could add full reconfigurability, which means you can get to any of these solutions. But then if many of the solutions have similar performance, maybe we should have had some limited configurability, because this choice and this choice both gave me the same performance, and this is maybe cheaper in terms of hardware implementation. So I think all of these questions are things we are also trying to answer, and that's where co-optimizing this, trying to understand the hardware cost for each of this is really, I think, a very interesting domain that has a lot of opportunity for future work. Yeah, a good question.
Okay, gotcha. But I have one more question. Is that for the hardware schedule, we are only target for the task like the batch size equal to 1, or we can also target on a task that we have a lot of batch size and it's also a batch size parallelism.
Yes, so in this work we were only targeting batch size equal to 1, but so Felix had some follow-on work where he was actually looking at a larger batch size problem as well for this, and he has that under submission. But in general, yes, like there isn't. So the specific problem is kind of abstracted out, right? So we can have more batches, lesser batches, and I think that might just change the specific solution you come up with. And what you find is most optimal. So if you have a batch more than one, then there's another reuse angle that has come in, and so you might want to in terms of pipeline parallelism, you might want to kind of save some of the intermediate outputs and reuse them in the next layer. And if you have fewer batches versus large batches, and with large batches maybe the entire layer is something you want to run and just run all the batches together. So again, the design space, I would say, would increase, but the technique itself will still work. Like there's nothing that's in the technique that's restricted to batches. Similarly, I was showing convolutions. You can run gems, right, which have 3 loops. So maybe the design space is somewhat smaller here. In convolution, there were 6 loops, right? So all of this is will just change the size of the design space, but the technique itself will apply.
Okay. Thank you. Gotcha. Thank you, Professor.
I think we have a question, another question in the chat box.
Oh, in the chat. Let me read it out. So what do you think about making the search space more complex, like searching for quantization and neural architecture with the hardware? Would doing these searches individually make sense? And the search, and yeah, so that's an excellent question, right? So I mean, and yes, like I mean, in some sense, this work is just touched upon one angle, right? The DNN model was fixed. So we kind of started with mapping fixed, we only changed hardware. Then we had like hardware fixed, mapping change. Then I couldn't present digamma, it was trying to search both of them together. And yes, trying to also do neural architecture search for the architecture and quantization will make the search space even larger. So to your question about whether it's better to do this individually or together, it really depends. So today, a lot of this is done individually, partly because again, each of these search spaces is so large that doing it together is way more complex. So what a lot of people do is they'll kind of have some design here, like they'll come up with some architecture, do the search for the, let's say, hardware, then feed this back and then do the search for the software, right, for the model. So, but the problem with this, like doing this individually, is you might miss out on certain optimal points, but it's easier to implement. What we would like to do is actually try to do the entire search together, but that will mean like a method that can capture all of these pieces together. So if I do encourage you to check out our digamma work, where, I mean, we initially were trying to do the mapping and hardware search separately and put them in a loop, but then we came up with a mechanism where we could do them together by just encoding it as genes. So I think what was pretty cool there was, within the same method, like one more gene kind of now corresponded to hardware. I mean, maybe, you know, we have more genes that now correspond to model characteristics, and we can tune all of them together. I don't know if it'll work, like what are some of the challenges, but I think what the key takeaway would be that rather than just creating this large genome and just randomly having a method search through all of them, this is where the domain knowledge piece comes in, where maybe for the genes that are related to the model architecture, you try to perturb them in a different manner, because you know that, you know, CNNs, you know, will kind of evolve in this manner. And similarly for quantization, like have certain, I mean, so as long as you kind of maybe have the operators tuned and then define the entire problem as one piece, it should be possible to do it together. But again, I'm kind of just throwing this off the top of my head. We haven't actually tried this for the model, but overall, I think if you can do everything together, will make the most sense. But I'll also caution that if you do the whole thing together, you've kind of designed one thing that's very, very specific for a specific, right? You have a one model, best mapping for it and best hardware. But if you want to design something that's more general, then it becomes a challenge. So which is why maybe doing them separately makes sense, where you first do this, come up with the best hardware and map, I mean, you know, whatever accelerator architecture. And yeah, I mean, for that, try to find the best model, right? So that will kind of give you more, you know, like it'll be more widely applicable. But if you really wanted to design the best thing for one model, then doing it together makes sense. So, I mean, that's, I guess, an interesting trade-off. Yeah. Yeah, good question.
I just come up with another question. For the gamma work, just for certain hardware, we're targeting to design a data flow. I think for that task, maybe the optimal solution exists. Just we have a unique optimal solution, since we can theoretically try all the possible.
So as I was saying, it is, but it's still very expensive to search through all, because there's a lot, as I said, there is a, I mean, I mentioned, right, there's like millions of choices.
I understand that, but so our gamma work is, we also can find that solution, but shorter the search time, or we shorten the search time and we get a suboptimal solution.
Yeah, that's a good question. So actually, let me just again quickly share my screen again. So this is something we are trying to understand. So, and like this chart is trying to show that. I hope my screen is visible. Yeah, so like this is exactly what we were trying to understand, where, you know, so this is the, let's say, the entire design space that I've plotted. And these are the colors are representing how good and bad. And then for each method, you know, let's say gamma is these green ones here, you know, PPO, this RL is this one. So this will allow us to actually tell us whether or not gamma found. So if there is a point here, which is better, then we know that, oh, RL found it, gamma didn't. But if there's a point here and which is identical to the point here in terms of performance, let's say the same color, then yes, gamma found one optimal, RL found a different optimal, but they are the same performance. Or maybe gamma didn't, right? In this case, you know, this method here, I forget which one, this brown one is PSO. So this one is actually something that is not finding any optimal value, because all the optimals are here. So this method is just not working. So again, we are also trying to understand this. And we are thinking that maybe visualizing it might be one way of doing it, because otherwise, yeah, you can imagine that just kind of going through all the data and figuring out whether it's optimal is a challenge by itself. So yeah.
Okay,
so that's a good question.
This picture is very clear. Oh, I got it.
Yeah.
Other questions from the audience?
Yeah, Professor, my question was very closely related, like associated with what one just asked. And I was also kind of wondering, like within, like in the gamma model, in the gamma, which you showed, like you're adding certain more stages beyond the normal as far the genetic algorithm is concerned. By adding just those more stages, did it not make the like model more specific again, or like was it generalizing? What were your observations during that?
Yeah, no, that's a good question. So in some sense, we've made this model or the mapper very specific to this problem of finding mapping. So gamma is not a generic genetic algorithm anymore. Like you can't apply it for any other problem, but it's only applied for the problem of finding mappings on an accelerator. And so in that sense, it's more, but within that context, it can now search for the entire mapping space for an accelerator. So, I mean, in some sense, what we are now trying to do is, yeah, specialize the search algorithm to work better, because the search algorithms otherwise will, because the search space is so large, like we, as I said, right, like in the extreme case, you could just do exhaustive through everything. That'll work, but you just don't, that's just not going to, finish in time. So hence we are trying to develop a search method that's more specialized for this problem domain. And with that, it's able to find the best solution much faster than alternatives. That's really the way to think about it. Yeah.
Thank you.
But searching itself, just the other thing to remember is now, because the genetic algorithm is also running, so there's a time taken by the genetic algorithm and there's a time taken by Maestro to evaluate how good a mapping is, right? So now the search time includes this plus this, and while if I did not have the genetic algorithm, I had just exhaustive search, that part might have been faster. So there's this trade-off where, it is taking longer to compute and evaluate each point, but it needs fewer points to get to the optimal. While in some other methods, you are kind of just searching randomly. So there's no time, there's no algorithmic time, but you just search too many points and you're not really sure if you'll reach the optimal. So again, all of these I think are interesting things to keep in mind in terms of search time. So if you were trying to do this at design time, it's good. If you were trying to do this at runtime, right? If you wanted to use Gamma as a runtime scheduler, then there's a problem, because you probably don't have enough time to run for 20 minutes to come up with the best mapping, right? So you can't run it in a compiler, you probably have to do it. So these are, I think, some of the things to also keep in mind. I mean, it's going a little bit beyond your question, but maybe I just wanted to kind of present this big picture, right? On how that's the trade-off. These methods are good for design time. And that's why I was mentioning this notion about generalization or one shot, where maybe you run it once and then in the compiler, you came up with the best mapping for ResNet and now you want to run some other model. There you don't really have time to run the entire search again, but you just pick the search value from the previous one. That might still be better than the compiler just thinking of some simple heuristic, if that makes sense.
Yeah, thanks.
I think there's another question.
Yeah.
So most methods tune the compute part of the accelerator to improve hardware efficiency. With the emergence of more memory-bound workloads, recommendation transformers, is there a possibility of enriching the design space so that these workloads are also optimized? That's an excellent question. So yes, in all of this, including our work, we kind of assume that we are not memory-bound. It was all about compute-bound, compute efficiency. But once you actually have things that are way more memory-bound, then yes, that's something also one needs to take into account. So there might be mapping. Actually, let me take that back. So we did assume things were, we did run transformer models as well, which were memory bound. So you will, let me paraphrase that. So Gamma in that case will find a mapping that maybe tends to optimize more on chip reuse so that you are not as memory bound. So in some sense, the mapper is going to try to find a solution that will overall optimize runtime, and it will find something that is trying to, not have too many memory accesses. So either for energy or for performance. But your broader point is still true, which is the fact that I think for a lot of these memory bound workloads, we have to maybe do a little bit more of a, thinking about how to optimize the accelerator space and the mapping space. And are there other mechanisms we need to use to either get more reuse or try to do some clever scheduling to hide delays better and so on? Yeah, it's a good question.
Other questions from the audience? If no more questions, so I have several questions to ask.
Yep, go ahead. Yeah.
Some of the audience already asked some of my questions. And I have one question. So I remember in your first 1 or 2 slides, you mentioned that so actually we have the different type of the DM models, right? And so one's very important type is the sparse, right? Mm-hmm. And we know that the systolic array is not very good at dealing with the sparsity. So do you think that from this type of design space exploration, whether we can find some good solutions to help the systolic array to process the sparse models?
That's such a good question. So the funny thing is, right before this meeting, I had a meeting with Felix where we were talking about exactly this. So it was like, hey, how can we extend gamma for sparse? And so I think there's a couple of, so I would say that, like, from a systematic perspective, yes, right? So what you would now need is, you need a cost model that can like model sparse, which is something that's a little bit more challenging because sparsity is often highly like data dependent. So one is, I mean, especially if you're dealing with activation sparsity, that's data dependent. Even for weight sparsity, like if you wanted to do it purely in an analytical manner, it's more challenging, right? So one of the things we are leveraging here is the fact that the cost model is analytic, so we can very quickly, you know, find a point, ask, hey, how good is this? Like if you had to run a full cycle level simulation for the sparse part, then that's more challenging. So I'm just trying to generally say that some of the challenges are the cost model itself for sparsity, if it's, you know, given that it's data dependent. So that's a challenge. But okay, so suppose you did have some way of modeling the cost for that, then yes, methods like this would work. We believe that, you know, at the very least, if you have a sparse accelerator design space, maybe the mapper will automatically find mappings that are optimizing for it naturally, or maybe the mapper itself needs to have some additional information. So let's say in the genome, I have a gene that is deciding maybe some other specific parameters for the sparse accelerator. Okay, what should be the compression format, like CSR or CSC, and what should be? So they might be, again, these are things it should be possible. I think it's just maybe related to the previous question. I think the design space increases even more, or it has even more knobs. So I think as long as we can capture them, again, whether with RL, with actions, or like with GA, with genome, whatever the mechanism being, but as long as we can capture it, it should be possible. And I think that's definitely an interesting area which hasn't been explored. I think, so just like dense accelerators went through a phase where people hand design things, right? So Iris and NVIDIA were hand designed, then people started automating it. Right now we're at a phase where sparse accelerators are being hand designed. At least commercially, there's not even ones that exist except for, you know, NVIDIA A100. Like commercially, there's no sparse accelerator. Research there is, but they're all hand designed. But hopefully we'll get to a point where, you know, we can also automate that. But yeah, as I said, the challenges there are more that a lot of times it's data input dependent. So I'm not very sure how one will have to do it. But yeah, it'll be interesting. Yeah, that's a good question.
I have one question. Can I ask?
Yeah, sure.
Yeah.
Like Dr. Tushar mentioned about in sparse case, what if we go at multiplier level? I mean, inside PE, and we make different chunks of multipliers, and then we try to make something with reinforcement learning, incorporate with power intent model like UPF at at ASIC level. I'm not talking about at FPGA level, but at ASIC level, we can incorporate reinforcement learning with UPF.
Yes, so I think I agree. So I as I said, I think in terms of the design space itself, yes, like you can now think of a sparse accelerator with some additional components, right? As you said, like you maybe break a multiplier into smaller components and have some way of so that comes into the cost modeling piece where like you need to have an accelerator design template in mind, which has more components than the dense one. And so that's one thing. And now the second question is, how do you tune those? And I think my general point was that if sparsity really depends on the input, then yeah, maybe that's fine, right? So I mean, right now we ran ResNet, right? And we came up with the best design. But here there might be 20 versions of ResNet, each with different amounts of sparsity. So maybe like, do you then tune for each? Yeah, again, it should be possible to do. You're right. Like, I mean, you just model it as some kind of, as I said, GA or an RL with more components and model it. But I was just saying that in terms of challenges, just remember that this design space will be even larger. And since a lot of this is dependent on the input, trying to do it at design time before you tape out the ASIC might be challenging because you don't know what the sparsity will be when the actual chip comes out. So just something to keep in mind.
Yeah, thank you.
Yeah.
Other question from audience? Okay, and I have another question. And it is also about the design knob. So as you guys show that, so we can analyze the entire like convolution using the like 7 loops or the 9 loops, something like that. And so I was wondering, so because for many state-of-art CNN models, actually we don't use like the vanilla VGG like or the AlexNet like topology. This is more about the topology level, like the chart, and we have like DenseNet has some complicated and so on. So I was wondering whether we can also consider to explore the design of for the topology of the network model. We know that there are some right now. There are some papers that the hardware and the model co-design NAS to explore that, and but it's still kind of based on search. So I was wondering, so the design, the topology knob itself, when we have that, is a fixed. Like for example, we have the fixed the transformer or fixed the ResNet, and we do not only consider kind of the granularity at the 2D convolution this level, and we also consider about is the overall topology.
Yeah, so that's a good point. Yeah, that's actually a great point. So I think so you're, if I understood correctly, there's kind of 2 questions here, right? So one is so one is we can of course change the topology itself, but you're saying that even when we are mapping, like if we are a little bit more aware of the, like right now we just did layer by layer and each layer is convolution, but there is like, residual layers, there's skip connection. So yeah, I think that is an interesting space that we haven't yet explored, but it should be possible to do. So trying to kind of, I think it kind of comes to this view. And again, like, I mean, apart from our work, I've seen papers that are trying to, look more at like mapping the entire model, in which case, the way I view it is, I think the design space for the map space is even larger. It's not just about one operator and all the choices. Like you have all the layers, and like, there's, how do you again slice and dice across layers? Maybe you map 2 layers at a time. Maybe you, is this, I mean, there's a residual connection. Like how is that getting accounted for? That might be very, very interesting to look at. You're right. I think that space. So even before sparse, I would say that's a space that hasn't been explored too much by automated mappers, because I think automated mappers are still focusing layer by layer. But that's an excellent point.
And also, so for the transformer, we know that right now it's very hot for the algorithm community, but for the hardware community, especially for the design automation, so we have not exploited well. Do you think that because we need to wait till the mode of the transformer become converge, like the so do you think that is the main reason?
That's a good question. That's a good question. I don't think the design automation so I think one is just the fact that since transformers is very recent, I'm sure that over the next year we'll see a lot of work. Like, I mean, already seeing papers related to transformer accelerators. So as I said, very natural, right? First, people will come up with accelerators optimized for transformers. Then people will start looking at efficient mechanisms for, design space exploration. So maybe it's just the timing thing that's not reached. But I do agree, there is a challenge where for transformers, there's not a very clear, like, converged architecture yet. Which but I mean, I think even CNNs kind of, people went from accelerators for AlexNet, VGG and so on, coming to ResNet, and during this time people came up with nice data flows and accelerator knobs and tools. So I can imagine the similar thing happening here as well. But I think it's just not a lot of people have, or even if people have gotten into it, I don't think those works have come out yet, which is why maybe we've not seen. But I have started seeing more and more works in that space.
Because I think one reason is because as compared to 2D convolution, the kernel computation of the transformer is just kind of it's kind of simpler. It's just the GMM. So the play space for the designer to do some of the kind of very delicate design is kind of the relative smaller than.
I think there you really have to, again, related to your previous question, you really have to look at maybe the full model, because now you have a lot of, some of the components are more memory bound, and so you kind of have to optimize at that level. Individual like layer by layer is probably, as you say, just a gem, so it's kind of no different.
And my last question, actually it's very specific to you because we know that you are the expert in NOC. And I was wondering, have you ever considered about also explore the NOC as a design knob in your entire design space exploration?
Yeah, good question. So kind of. So the thing is that so every time I said, this data flow and that data flow, each data flow needs some kind of an NOC support to enable it. And so if I have some like data flow or some mapping where I have, spatial reduction happening, then I need some like support for, doing the reduction spatially. If I have a data flow where it's purely output stationary, there's no communication, then I don't then I only need connections from the PEs to the buffers. I don't need local connection. So in some sense right now, the NOC knob is coming, but it's coming more as, right now in our exploration, one knob that comes is bandwidth of the NOC. And the topology in some sense, we've somewhat abstracted where we said, okay, yeah, if you want this support, you have this kind of a maybe support that you need and so on. So we have been doing that, but it's not a very explicit knob. It's more implied by the kind of data flow. If that
Okay.
makes sense.
Okay, I see. Okay.
Yeah.
Okay. Thank you. Thank you very much.
Yeah.
And we have very hot discussion this time.
No, great. Thank you guys. The very, very, very good questions. And I really enjoyed this. Yeah. Sorry for, exceeding a lot of time, but I think, but yeah, I'm happy that all of you understood, like, despite me going so fast with all the questions, I can see that people understood. So I'm very happy. Thank you so much. Yeah.
Thank you so much for being here. And also thank all our audience to attend our this semester talk. And actually this is the last talk in our this semester's
I see.
in the talk. And thank you all of your support. And so happy New Year to everyone. Happy holiday and see you next spring.
Yep. Yeah. Thanks, Bo. Again, thanks for the invite. Thanks, everybody. Yeah. Happy holidays. Happy New Year. And yeah, see you all next year. Hopefully, like in person at some conference.
Yeah. Hopefully. Okay.
Yes, yeah.
Thank you.
Yep.
Have a wonderful day.
Thank you. Yep.
Thank you,
Bye.
everyone. Thank you. Bye.